Welcome to Lecture 4, Video Lecture 3. Lecture 4 means we're a quarter of the way through the semester. That's hard to believe, but once we get to the end, we will be a quarter of the way through. So, here we go. For Class 4, we're going to cover basic states of stress, forces, resultants, and components. This class particular will do a lot of practice problems during our in-person lecture. It's really important to practice lots of these. That's how you get good at it. We're also going to talk about point loads, uniform loads, and area loads. That was a real struggle for last year's class, more so than the previous years, so we're going to hit those pretty hard. So stress, what is it? If you look it up in the dictionary, pressure or tension exerted on a material object, or a state of mental or emotional strain resulting from adverse or very demanding circumstances. So two really different definitions. What we're talking about in this class is the first one. So pressure or tension exerted on a material object. Stress, forces are applied to a body. Stress is the internal reaction or the resistance of the body to those forces. So in this case, in the human case, if you're taking a test, the test is the force. The stress is how you feel because of the force. The stress is the internal reaction to the force on the body. Looking at the human body on a structure, and you see that forces are applied to a body. So in this case, the force is the barbell with all the weights. The stress is the internal reaction of the body builder or weightlifter here on the right. The body is being crushed by the weight, right? It takes stress. You have to really exert effort to lift that much weight. The stress is the internal reaction or resistance of the body to the force that's being put on it. So in structures, there are 5 basic states of stress. Tension, something is being pulled or elongated, stretched, trying to rip apart. That's tension. Compression, where we're crushing something, we're squashing it, we are trying to compact it. That is the state of compression. Shear is when we're slicing it, when we're trying to take 2 pieces and pull them in opposite directions in a slicing motion. Torsion, when we're twisting something, think about wringing out a wash rag or a towel. That's a torsion motion. Turning a screwdriver is a torsion motion. And then bending something, exactly like it sounds. You want to bend something, you bend it. You might want to bend a paperclip into a certain shape. That's exactly what we're talking about. It's when you're bending something. Looking a little bit deeper, all these examples are with ropes, but tension doesn't have to be with rope. It's anything being stretched or pulled apart. Tension force creates tensile stress. That's the internal reaction, and remember that's a pulling, trying to rip something apart. Compression stress, body is being crushed. So in this picture on the right, there is really no body, but the clamp is to imply that a body would be crushed by the clamp, tightening of the clamp. On the left, the chair is being crushed by the person sitting in the chair. So the chair is in a state of compression, not the person. So it's something being crushed, and it creates compressive stress. Shearing, this is what is difficult to explain. This is the hardest one to explain, but it's where a body is being sliced or pulled in 2 different directions perpendicular to its longitudinal axis. So in this situation, a bolt is being sheared. So this bolt might be part of a gusset, a trailer hitch tongue, if you will. How the trailer pulls one direction and the pickup pulls the other direction, and if you slice through the bolt, you end up with a failure that looks like this. That's shear failure, also causing shear stress. Torsion, I mentioned both of these 2 things, but the body is being twisted. It's a rotational shear stress. So really the stress is happening on a plane that's perpendicular to the longitudinal axis, just like a slicing, except for we are slicing in a rotational direction instead. So twisting is torsion. It's rotational shear stress. bending, you probably don't remember this. A few iPhones ago, they had a big deal with them actually bending because they made them so thin. Couldn't pass up this picture even though I love Apple. But bending is when the body is being bent about an axis. Bending creates tensile, compressive, and shear stresses all at once. We'll go into that on the next slide, but those things all happen at once, all because of bending. So here's an example of bending in a beam. We're going to do a physical example of this in class, in-person lecture, but we have compression stress on the top of the beam if the beam is bending like shown. Smiling creates compression stress on the top, tensile stress on the bottom, and shear vertically slicing up and down all the way through the beam. Shear all the way through the beam, compression at the top, tension at the bottom. All of that happens because this beam is being bent. Check the Blackboard for the Slido login number, but question break, what questions do you have? Ask them, vote for them. I don't want you to forget to ask those questions, so do it right now. Pause the video. Forces. Force is an action of one body onto another. So we define a force with three things. Think carefully about this. The application point, where the force is applied to the body. In this case, the application point, the guy is pushing on the file cabinet. So where his hands touch the file cabinet, that's the application point. The magnitude, how strong is the force? Well, that depends on how hard he's pushing. So the magnitude is him, essentially. It's how hard is he pushing. The direction is which direction is the force pointing? Which direction is the force pushing on the file cabinet? Which direction is it pushing on the body? And in this case, it's to the right. So the direction is to the right. So we have three things that define a force: the application point, the magnitude, and the direction. We'll look at a couple more examples. This situation, we have an application point, magnitude and direction, just like before, but this one, the most important thing is the application point, right? If you want to help this tree stand up straight, you probably don't want to pull on the tree with a stake and a tether at location 2. It's not going to help you very much, right? Because you want to get as far away from the base as you can, because that's where you can have the most effect on the tree. We'll talk about why later in the semester. So the application point 1 is really important because 2 wouldn't do us very much good. We won't be able to straighten straighten the tree using application point 2. The magnitude of the force, also important. In the picture on the left, we're moving a bus. Probably going to be a lot more magnitude of force. Also takes a lot more people, obviously, by the picture. On the right, we're moving a beetle, looks like. Not quite sure if that's a beetle, but we're moving an old car, simple car, not a bus. One person is moving a car. Now, we don't really know if these people are actually moving the two vehicles, but the point is that the magnitude is important and various magnitudes are needed. Direction is also important. In this case, the basketball. If the direction is in the red arrow, this person will miss the shot. If the direction is in the green arrow, this person will make the shot. So all three pieces are really important to note because they have quite an effect on the behavior of the body being acted upon. We'll look at that after a question break. Questions? Go right now. Slido.com. Enter your questions. Vote on what's there. So let's look at some forces. So pay attention here to the line of action of the force. Okay? We talked about the direction of the force and the application point. So the line of action kind of combines those, and we say that the force is acting on this line. As far as this file cabinet is concerned, pushing from the left side and pulling from the right side have the exact same effect. These two situations are equal as far as the file cabinet is concerned. Now, just to caveat that, of course, the safety people don't want you to pull on a file cabinet because they don't want you to tip it over on yourself. But pushing or pulling, the file cabinet is still going to move because the line of action is the same, the magnitude is the same, they have the same effect on the file cabinet. Now when you combine forces, so we have a force on the left pushing to the right and a force on the right pushing to the left. We say they're equal, we say they're on the same line of action, and we say that they're opposite directions. So we have our three things that we're worried about, and the net is simply zero. So the file cabinet is getting squished, but as a whole, it doesn't move because the net force is zero on the file cabinet. So file cabinet might be seeing some compressive stress, but it's not moving, it's not feeling a force globally, it's actually zero. The two forces cancel out. If they weren't on the same line of action, they would not necessarily cancel out. If they weren't the same magnitudes, they would not necessarily cancel out. So we have a special case here. Here is the similar situation, except for the force on the right is now pushing to the right, just like the one on the left. So they're no longer canceling out, they're actually adding together. Same line of action, same magnitude, so the force on the right is twice as much. Again, as far as the file cabinet is concerned, it doesn't matter whether the force is acting on the right or the left of the file cabinet. It's the same thing as acting doubly on the left side of the file cabinet in the picture on the right. So these two situations are equal. Question break. Those things that we just went over are the building blocks for the rest of this lecture and the rest of the course. So make sure you understand them. Go back and watch it again if you want to. Ask your questions. Ask me questions in class, but don't forget to ask the questions. Don't forget what they are. Okay, this is the next step. So we talked about what happens when the forces are on the same line of action and the same application point. But in this case, they're not on the same line of action. So what do? We have A, which points up and to the right, and B, which points down and to the right. And these tugboats are actually towing a submarine. Probably not very likely, but you know, it accomplishes the goal of talking about forces. So what do? We use vector addition. Hopefully you learned that in physics. If you haven't learned that in physics, it's okay, because we're going to go over it again. So this will either be a review or a very aggressive learning for the first time of vector addition. Vector addition graphically can be said just like this. We put tip to tail. So if we have A plus B, we put A where it is, we move B to the tip of the arrow A, and then we add those two together by connecting the tip to the tail of the two overall. Now notice that I didn't leave the B where it was, I moved it, so you don't have two B's, I just moved it. I wanted to do that slowly over a couple steps so you could see what happened. The B has the same direction. It has the same magnitude. We're just moving the application point to the end of A to get the sum of the two forces. So the sum, like I described, but it's easier to see in this picture, is from the beginning point of A to the ending point of B. So when I add two forces together, I put them tip to tail, and then I connect the two ends, or three ends, or five ends, or however many forces we're adding. So what you see is that force C pulls strongly to the right, and the up of force A cancels the down of force B. Those are opposite, those are equal, so they cancel each other out. All that's left is the pull to the right. So taking a look at the forces in close-up, we have A plus B equals C. Some terminology for you. C is the resultant of A and B. C is the resultant of A and B. A and B are the components of C. So it takes A and B to make up C, and C is the resultant of A and B. Some of you are wondering, Does it work the same if I said B plus A? Well, let's find out. I'm going to move that arrow over. A, remember? Same direction, tip to tail. There we go. I moved the whole arrow instead of copying it. A plus B, connect the tip of B to the beginning of B to the ending of A. We end up with C. C is exactly the same as before, so same magnitude, same direction. Zooming in on those forces, writing the equation B plus A equals C. And now if I put those on top of each other so you can see A plus B equals C, B plus A equals C, those are the same. When you're adding vectors, you can add them in any order you want. Questions? So the next question is, can forces be subtracted? Well, I told you they can, right? Right there. Forces may be subtracted. So in this case, we have C minus B. All right, how do we do it? We put the tips together. We flip the B. So let's take a look at that. I have C. I have B. I'm going to flip the direction because C minus B is the same as C plus a negative B. A negative B is simply the reversed arrow, so I'm going to flip that B over so the arrow head is on the left side. So if I have C minus B, what do I get left over? Looks like A, right? Yeah, so C minus B, or C plus a negative B, is equal to A. So the good question is B minus C also A? B minus C, do it in your head, flip that C, do you end up with A? There we go, flipping that C in graphic form. Lots of you are saying, yep, we end up with A, but wait 1 second. We can't forget that we have to start at the beginning of the arrows that we have left and go to the end. So in this case, the beginning of the arrow is at the point of B, the bottom there, and it moves to the left, points up and to the left. So B minus C is not A because A points down and to the right. But it is pretty similar to A. The only thing is it's negative A. So B minus C is negative A. Now some of you are struggling with that. Don't worry. Slow down. Rewatch it. Try it out. But the math is exactly the same. Remember that A plus B equals C. So if I give you that equation and you wanted to find out what's B minus C, well, if I have B on the left side, I can subtract C from both sides. So I end up with A plus B minus C equals 0. Okay. And I want to know what B minus C is, so I need to move the A to the opposite side. To do that, I subtract A. So I subtract A from the left, subtract A from the right, and I get B minus C equals negative A, exactly what we got before. So the math works the same as the vector addition. Oh boy, what happens when we combine more than two forces? What do you think? Gonna say it out loud? Okay, enough time. Same thing. Tip to tail, tip to tail, tip to tail. So instead of only having two forces, in this case we have four. So I went ahead and did them in order, alphabetical order. So I have A, move B, move C, move D. Doesn't matter which order you work in, you're going to get the same answer. So even though you might convince yourself that you won't, try it out, you will get the same answer. So once we're done stacking them or putting them in order, tip to tail, we start at the beginning, we go to the end, and we end up with E. Force E starts at the point where all the applications are, and it goes to the end of the last arrow. Zooming in on only the forces and writing the equations, we say A plus B plus C plus D equals E. Alright, what questions do you have? That's a really important piece, so make sure you understand it. This lecture is really, really important. It's really the meat of the class. So, we're adding forces. And the truth is, if you don't have a nice scale drawing, and I didn't really have a nice scale drawing, but I had an okay drawing. But if you don't have a nice scale drawing that show your forces to scale, your arrows to scale, so that you can't, graphically move them, how in the world do you figure out what your resultant is? Well, this is where we use math, and this is where we use components, and this is where we use that right triangle that we talked about at the beginning of the semester. So, you remember that a resultant can be the sum of two forces, or any number of forces. In the same way, we can break down a force into two or more different components, which add together to make the whole, or the resultant. So what if in this case, A and B were resultants, and we wanted to find subcomponents of A and B? Could we do that? So hopefully on the last slide you thought about, could we do that? If you did, hopefully you said yes. So we have A. Let's look at A only. We want to break it down into two components. What about that right triangle? Then what we end up with is AX and AY. So AX is the force component that moves from the beginning of A to the right only in the x-axis. AY moves from the tip of X up to the arrowhead of A, the resultant, only in the vertical y-axis. So AX is a component of A, AY is a component of A, and A is the resultant of AX and AY. Don't worry, I'm not going to go through that again, but the same is true for BX and BY. If that was confusing to you, back up to the last slide, listen to it again. In each of the cases, we can break the force down into smaller components. So why would that be helpful? Well, if we don't have a graphical drawing, but we know that we can add things in the same line of action or the same direction, then suddenly we know that BY and AY are in the same direction. They're both in the Y direction. And BX and AX are in the same direction. So now we can do the math without having to do the graphics. So in this case, we have component plus component equals resultant, which used to be A plus B equals C. But now we've broken A and B down into subcomponents or smaller components, AX, AY, BX, and BY. So what we can say is that AX plus AY plus BX plus BY equals A plus B, which also equals C. You can see I have two graphical depictions here, one on the top of C, which is A plus B, and one on the bottom, which is BY, BX, AX, AY. You notice that the BY and the AY cancel each other out, right? They're both in the Y direction. One goes down a certain amount, the other one goes up that same amount back to the zero horizontal. Now, just a little note here, components can be any direction you want, so long as they equal the resultant. So these three resultant arrows are exactly the same. All I did on the right, it doesn't look the same, right? It looks longer. It's not. It's exactly the same direction. It's exactly the same magnitude. I just broke it into different components. I turned the axis to show you that you can do that. So you don't always need to think of your x-axis and your y-axis as being horizontal and vertical. You can make them whatever you want, as long as you use them consistently. If I plot those on top of each other, you'll see that, yep, sure enough, those are exactly the same. In the components, both sets of components, both pairs of components, add up to the resultant, the same resultant. Doesn't matter which axis you use. Now in this class, I don't think immediately I can think of any exceptions where we wouldn't use the x as horizontal and the y as vertical. So I'd probably suggest you get used to using it consistently, but just remember, you can break it up however you like. So what do you suppose the magnitude of those components are? How do we find them? Oh, that's right. We go back to the laws of trigonometry, the rules that we used in the first class of the semester. So if we know that we have a force that's 10 pounds up and to the right at 30 degrees from the horizontal, I can use 10 pounds cosine of 30 degrees to get 8.66 pounds, the horizontal component, and 10 pounds sine of 30 degrees to get 5 pounds, the vertical component. This is how we determine the components of the resultant force. Okay, that's getting to be a lot. So if you're confused, having trouble remembering or understanding, make sure you go back, watch it again, ask questions, Lido.com. Can't wait to hear. Go ahead and do this practice problem. Push the pause button. It's cheating if you play through. We have the Jumbotron at Cowboy Stadium. The pulleys B and C are being used to lift that Jumbotron. I'm making up this problem. I don't really think there's these small pulleys holding that thing up. But the point is, each of them has the forces shown. So the question is, determine the horizontal and vertical components of each force. That's the first part. So here I gave you angles. That left one does say 14, not 4. And I also give you magnitudes. So what I want you to do is figure out the x and y components for each of those forces A, B, C, and D. Pause the video, figure it out. I'm telling you, if you want to understand this, you have to do it on your own. You have to write it down. You have to calculate it. You cannot just watch me work the answers. It will not work. Looking at the pulley on the left, we get force A and force B. I'm going to go ahead and say AX is 1,000 pounds times the sine of 14 degrees, and that's 241.92. Remember, it's pointing to the left because that's the direction that A is pointing in the horizontal direction. And remember, we use the sine because this is the angle from the vertical, not the angle from the horizontal. As far as AY, which is pointing down, 1,000 times the cosine of 14 makes 970.3 pounds. And then we move on to BX and BY. You can see BX is 1,000 times the cosine of 36, 809. And BY, 1,000 times the sine of 36, that's 587. In the case of B, BX points to the right. Remember, it has to start at the same place and be moving towards the end. And BY points down. I'm not going to walk through each of these, but you can see the calculation there. You figure out which direction it points. Make sure you put them tip to tail so that they start and end at the same place as C and D. So you figured out the components of each force, but now we want to ask the question, what is the resultant force on each pulley? So each pulley has two big forces pulling on it and 4 components that you figured out. I want you to tell me what's the resultant. So remember, this is what we started with. AB on the left, CD on the right. Tell me what the resultant is for each of the pulleys. If we look at the pulley on the left, we have ABX and ABY. That is what we're calling the resultant. AX points to the left, so it's negative. BX points to the right, so it's positive. Now, those are both in the X direction. They have the same point of application, ends up being the center of the pulley. They have the same direction, both in the x direction, so they can be added together simply. We have minus ax plus bx, we get a total of 567. Do the same thing with ay and by. In this case, they're both pointing down. So we have ay plus by. They're both pointing down, so the resultant is also pointing down, and it's 1558. Now, don't forget it's important to know that direction. So you got to use the arctangent or inverse tangent to figure out what is the angle from the horizontal. You can use that by drawing out those components, figuring out what their magnitude is, and then using the inverse tangent to get the angle. Finally, we have those components. We need to know what the magnitude of the resultant is. So we need to use the Pythagorean theorem, a squared plus b squared plus c squared, a squared plus b squared equals c squared. So work out this math. That's what I'm doing here. AB is c in that Pythagorean theorem. ABX is a, ABY is b. So those two squared, we got to square root both sides to figure out what the resultant is, and we find out that the magnitude is 1658. I'm not going to so carefully walk through this one. It's exactly the same thing on the other side. I have confidence you can do it on your own, so please work through that. All right, do you have questions? Were you able to work through that? Was it difficult? Where did you have difficulties? Put those into Slido. What's still confusing? What did I not explain well enough? Put those into Slido. Vote on other people's. Add your own. Create new ones. Whatever you like to do. Don't forget to ask the questions. All right, I want you to work this one on your own. I'm going to not talk through it. The video will play through the next slides to show you the answer, but seriously, pause the video now, work through the problem on your own. Check the answer. If you don't work the problem on your own, you will not learn this. I cannot stress that enough. Okay? So Team A and B are playing tug of war. Team A has given B the advantage of having 2 ropes and 2 extra players. Which team is winning? You have to figure out how you can combine these forces to figure out which one is actually winning. Okay, hopefully you got Team B. If you didn't, put the question in the Slido. What did you not understand about that? What do you need help with? Tell me. Question break is coming up. All right. Here's another problem. This one is a little more challenging. We want the net force of these 2 tugboats to be 10,000 pounds to the left. So what I want to say is that we need to pull to the left or up with 10,000 pounds. We need the resultant in the y direction to be 10,000 pounds. So I told you that each tugboat pulls at 20 degrees off the center line of the sub. How much harder must the left tug pull than the right to create a net difference of 10,000 pounds? So figure out how you're going to work the math to get that to happen. Figure out what you need to do. Figure out which components you need to use. Work through that, and then watch the rest of the video. So pause now. Did you pause yet? Make sure you do it. Pause now. Work that problem. It's a hard problem, I know. I have faith that you can do it. I know you're capable. Okay, you don't necessarily need to do this, but I said, let me just say that the right tug pulls at 100,000 pounds. Let me just say that. Okay? The force to the right then is tug right times sine of 20 degrees. That's giving me the force down in this picture, or to the right from the submarine's perspective. Hopefully that's not confusing. That's the force down. If you're a captain on the submarine, you're looking to the right. That's down on this slide. So what we know is the left tug must pull 10,000 pounds to the left greater than what the right tug was doing. So tug Ly has to be equal to tug Ry plus 1,000 pounds, right? So we know that that has to be 44,202. Then we can find out what's the force of the tug. Okay, what's the total resultant force? We do a divide by the sine of 20 degrees. We get the total tug left to be 129,238. And now we simply use the difference between the two. We started with 100,000. We have 129,000. So we know the difference is 29,238. Now you don't have to put in 100,000 pounds. You can put in anything and you will get the same difference. Here's an example of not putting in anything. All we need to know is to say that the resultant has to pull 10,000 pounds to the left. So what difference in force ends up at 10,000 pounds different in the y component? So 10,000 pounds divided by sine of 20, voila, exactly the same answer. What questions do you have about that? That was a complicated problem. It's hard to think about. Not so bad in the math, just a little difficult to understand. So make sure you understand that problem. Go back and look at it if you need to. Ask questions if you need to. Okay? Okay, like I said, this lecture is one of the most important of the semester. It's really the building blocks, and this is an important concept. We're going to talk about force distribution, the difference between a point load, a distributed load, and an area load. I need you to think about the units. I need you to think about what this means. You got Robin Hood running through the forest. He's got a tree that he cut down to make a bridge over this creek. If Robin Hood is standing on the log, he's a concentrated force. All of Robin Hood is resting on his two legs, which are very close together. Let's say he weighs 150 pounds. It's pretty light, Robin Hood, but hey, probably doesn't eat very much. So the force is not spread out at all. It's concentrated directly underneath Robin Hood. Now let's say Robin Hood hears a bird and he decides that his best vantage point is to shoot up laying down on the log. Now Robin's 150 pounds is spread out over 6 feet. It's not a concentrated point load anymore. It's spread out over the 6 feet. So we had 150 pounds total. That's spread out over 6 feet. So we need to say 150 divided by 6 feet equals 25 pounds per foot. So in each foot of length over that 6 feet, Robin Hood has 25 pounds. If he's uniform distributed, his head might be heavier than his foot. But anyways, the force is spread out, 25 pounds per foot. If we multiply that 25 pounds per foot times the total 6 feet, we get 150 pounds total. That's all of Robin Hood, okay? So all of Robin Hood is still there. It's just spread out over 6 feet instead of being concentrated in one spot. So here's that picture we had in an earlier lecture. We have the joist girder. On top of that, we have the joist. On top of that, we have the deck. The deck applies the load to the joist at every single one of those flutes. That is a distributed load. It's spreading it out evenly and uniformly on the top of the joist. Okay? Distributed load, uniform load from deck to the joist. Now remember, the load path moves from the deck to the joist girder. When the joists sit on top of the joist girder, they are only touching the girder at one point. They are creating concentrated loads on the girder. They are not distributing it evenly. They are only occurring at every 4 or 6 feet, so they are concentrated loads at the joist girder. The same is true for the columns at the end. Those joist girders, they tie into a column at each end that is 1 point. So the force is getting ever increasing because we're accumulating all this load. We have a larger concentrated load from the joist girder to the column. So the column is loaded from the joist girder. The column is loaded by the joist girder. So the joist girder puts a force, a concentrated point load, on the column. Okay, so we have uniformly distributed loads, but distributed loads don't necessarily need to be uniformly distributed. They can vary. So a great example of this is when we have drift on a roof and the snow piles up in the corner, we get an uneven or a non-uniformly distributed load. So it's still in the pounds per foot unit because it has pounds per foot. It's still distributed. It's just not constant. Okay. So here we have parapet drift on the left, uh, parapet drift on the right, which I didn't show any arrows, and then we have uniform snow in the middle. So we don't need to worry about that uniform snow. I mean, we need to worry about the uniform snow, but it's not variable like the one on the left. So zooming in on that little drift portion, we get larger um, distributed force on one side, the left in this case, and smaller on the right. All we're saying is that the magnitude of the uniform force changes over the length. It's still a force per length unit. The magnitude just changes. Okay, area loads take a step further, and remember we started with a concentrated load, and we spread it over a length, and it was a distributed load, and now we spread it over an area, and we get an area load. So these are forces of uniform or non-uniform magnitude spread evenly over an area instead of over a length. So in the case of this picture, we have people, 20 people in this conference room, each person's weight, add that together, divide it by the area, which is 30 feet by 12 feet, so we have 360 square feet. So the area load becomes 20 people times their weight divided by 360 square feet, or 4,000 pounds, that's the total people, divided by 360 square feet equals 11 pounds per square foot. So now we're having pounds per area instead of pounds per length instead of pounds. Okay, so we went from concentrated load pounds, distributed load pounds per length, area load pounds per area or square foot. Okay? Okay, that's an important concept, particularly the units. I don't want you to get the units wrong, okay? Units are going to be your best friend with getting the answer right on the exam, on all your homework. I had lots of students last year who still at the final exam weren't getting those units correct, okay? It's really important to pay attention to what that means. Pay attention to units. They're going to help you get the right answer. So please, 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 if you're confused about that at all, ask the questions. Okay, just a few notes on point loads versus distributed loads. So Robin Hood weighs 150 pounds when he's laying down and standing up. Globally, the beam reactions are the same, okay? So concentrated load and distributed load have the same effect on the reactions, those forces that are at the ends of the log supporting it. Locally, what the beam deflection does, what shape that log bends in, concentrated loads and distributed loads are not the same. They do not have the same effect on the log. So just to repeat, the forces at the end of the log are the same in both cases because concentrated loads and uniform loads globally have the same effect. Locally, that deflection, the log deflects more under the concentrated load than it does under the distributed load. So locally, they're not the same effect. So how do we create an equivalent concentrated load from a uniformly distributed load? Remember, we can't use that for deflection of a beam, we can't use it for that, but we can use it for determining what the forces on the ends are. So we have 10 pounds per foot uniformly distributed load, and it goes on for 10 feet. What's the equivalent concentrated load? How did we figure out what Robin Hood's total weight was? It's not too hard. We have 10 feet of 10 pounds per foot. So 10 pounds per foot times 10 feet gives me 100 pounds. Pay attention to the units. Do you see how the feet cancels out and leaves us with pounds? Exactly what we're looking for. So we know that the total force is 100 pounds, but we don't know where does it act. This is a uniformly distributed load. It makes a rectangular shape. When you have a rectangle, the concentrated load happens at the centroid of the rectangle. Actually, no matter what shape you have, the concentrated load happens at the centroid of the shape. The fact is, for a rectangle, it happens in the middle. So we have 10 feet. Half of that is 5 feet. So the concentrated load acts at 5 feet, and it's 100 pounds. Take a look at that graphically, and all of those blue arrows, 10 pounds per foot, can be represented by that 100-pound red arrow acting at 5 feet, as long as we're using it to determine the reactions, not determine the deflection, because local is not the same, global is. So I mentioned already that it doesn't matter what the shape is, it's always the centroid, and it's always the total sum of all the forces. So you can start to think of it as an area calculation, right? When we had 10 pounds per foot by 10 feet, we were multiplying the force times the distance, or the height times the width, to get the area of the rectangle. In the case of a triangle, we want to figure out what's the area of that triangle. So we have 10 pounds on the left, that's the height. The base in triangle terms is 10 feet, right? So we have base times height. And then triangle for the area is divided by 2. So we have base times height divided by 2, or 10 pounds per foot times 10 feet divided by 2. So 1/2 10 pounds per foot times 10 feet gives us 50 pounds. Again, the units cancel out, okay? Pay attention to those units. Use the units throughout all your homework, all your exams. It's going to make everything better for you. So where does the concentrated load act? Well, I'm going to tell you that the centroid of a triangle is 1/3 from the big end. So in this case, the big end is 10 pounds per feet on the left. So the location of the centroid is 1/3 from that end. So 10 feet divided by 3 gives us 3.33. And so we can know that the equivalent concentrated load for this triangular distribution is 50 pounds, located 3.33 from the left end, just like the picture shows. All of the blue is represented by the red for global reactions. Okay? Any questions on that? Go to slido.com, type them in, vote on them. We will be doing an activity. We're going to put some pennies or poker chips on a yardstick to look at the distribution, comparing concentrated loads to distributed loads. All right, that really concludes the lecture. If you have questions, make sure you go write them down. Like I said, we're going to do that activity in class, and I look forward to seeing you then.